All right. Let's go live. Let's make sure we're working properly. Okay, I think we are. Okay, so that was quiz 8. We will have quiz 9 tomorrow on chapter 10. Now, chapter 10 we're going to talk about today, but I'm going to hope and assume a little bit that you've been working on that already this weekend because there's a lot of stuff in chapter 10. But it will be on the exam on Wednesday, so we want to make sure to get a test on that first, so that'll be tomorrow. Tomorrow we'll get into chapter 11 a little bit, but that won't be on the exam, so it'll mostly be the quiz 10, and then some chapter 11, and then review. And then Wednesday's the exam. So there's no lab this week. We will kind of get a head start on the next week's lab. We'll talk about that in a little bit. We're getting down to the end of the class. Only 7 days left, including this one. 2 of those are exam days, so there's really not much more to do. We've got basically 3 more chapters to do in that time, or 2.5, I guess. So let's talk about chapter 10. So how did chapter 10 go for you this weekend when you were looking through it?
I thought it was good. I thought there were just a lot of different little things for each electron you know,
Mm-hmm.
molecular geometry for each, and remembering those names, and then
Right.
the bond angles and stuff like that.
Yep. So we'll try to organize that today.
I had a really hard time differentiating between electron geometry and molecular geometry.
Okay, that's fair, yeah.
The difference, but I forget which ones go to which category.
Yep, that can be tricky too. Other issues? Okay. All right, so as you read in chapter 10, we're start chapter 10 with what we call valence bond theory, which part of which is called the Vesper Model, which stands for valence shell electron pair repulsion. The idea is it's a theory of the reason why molecular shapes are the way that they are is because electrons repel each other, and therefore electron groups are going to want to spread out as much as possible, and so that they're as far away from each other as possible. It's a reasonable theory, and kind of makes sense, right? Electron groups will spread out from each other. And it does a good job of predicting the observed molecular geometry for a lot of compounds. However, as we'll see, it also breaks down, and there are situations where it doesn't work, and it doesn't predict what we actually see in real life. So then in the last half of the chapter, we'll talk about molecular orbital theory, which is a much more powerful theory that allows us to describe the electronic behavior in molecules in a much more useful way. That said, this theory, Vesper theory, valence bond theory, is extremely useful in the situations where it works. One of those is organic chemistry. If you're looking at compounds of carbon, nitrogen, kind of those second row elements, then this stuff works really well, and there's no need to go into a more complex theory. So that's why we spend time on it. And if you are planning to go on to take organic chemistry, definitely pay attention. This is one of those topics where the organic chemistry professors, we always everybody goes through the second semester Gen Chem class and then forgets all this, and then comes back and we're like, why don't you remember all this stuff? So remember all this stuff if you need to go take more chemistry, because it will come back. All right. So let me grab a table that kind of summarizes all this stuff, and then we'll go through it bit by bit and talk about it with specific examples. This picture is big, it's making it angry. Okay. So what this shows, as you've seen, is that once we draw these Lewis structures, we can figure out the overall 3-dimensional shape of the molecule just based on how many things are connected to it. So if it had 2 things, that's that first row, if you have a molecule that has a central atom and then 2 groups connected to it, and the theory is that those 2 groups want to be as far apart from each other as possible, then it's going to have a linear geometry, because the way to get those things as far apart from each other as possible is to make a line. Make sense? If you add a 3rd group, then you jump down to the next 2 columns, or the next row, and you make what we call trigonal planar arrangement, where you have the central atom in the middle, and instead of linear, it kind of pushes out to make about a 120-degree angle. Now, the reason that it goes that way and not, let's say, like a T shape, well, what do you think? Why is, if you have three groups, why is it trigonal geometry? Why is it not more like a T-shaped geometry? Yeah.
Because the two get pushed away from the one on top. A triangle is a stronger shape than a T.
Yeah, it's allows those things to be farther apart from each other. If we had that T shape, you'd have two like 90-degree interactions, and that would be closer. That would be more repulsion. And so we'd say, okay, well, instead of having those 90-degree interactions, we'll push those down a little bit, and if everything's 120 degrees, then it's a little more spread out, and it can be a little bit lower energy. That's the theory, and reality reflects that theory, because if we actually look at compounds that have three things attached, like BF3, we actually observe trigonal planar geometry with bond angles about 120 degrees. So the angle that the bonds make is about 120 degrees. All right. So you also see there's a second entry under the three groups. You see the structure SO2. Why does that molecule also fit in the same category with BF3 when we talk about the number of groups? Okay. The lone pair, right. So we would say that SO2, and I'll leave that up there and write on the board here. So another way that we can think of that SO2 is we can think of that lone pair on the central atom as occupying a space, much like an atom would. So that's why it's still considered a three group, and that's why this angle here that's made between from O to S to O is around 120. Okay, so a couple things about that. First, you'll notice in the table that it says that the approximate bond angle there for BF3 is 120 degrees, but for OSO, or SO2, it's a little less than 120 degrees. Why do you think it's a little less than 120 degrees? Guesses? First of all, let's refresh our geometry. Does less than 120 degrees means it's like being pushed more down or more up? Down, right? Because the smaller angle will be down. So that's saying that in this structure you actually have maybe like more like this. What might be causing that? Well, what's repelling more? Because they're closer together. Or I don't know who was first. Stefan, maybe?
I think one, since both of them are no longer equally electronegative, one of them's going to actually attract the other one.
These two?
Yeah.
They are still equal though, because remember that there's resonance going on here. So there isn't a double bond and a single bond. It's really like two hybrid similar ones. Kendall?
Is it they're more repelled by the lone pair than by each other?
Yes. So did everybody hear that? A lone pair has a little extra repulsion from an atom. And so whenever we have a lone pair occupying one of those groups, everything else is going to get pushed away a little bit more. And you see that throughout the rest of the table. Whenever you have lone pairs on the central atom, the angles get a little bit less than the others.
How important are the angle measurements for the purposes of the exam and knowing something
You should
like
know
that
these
is going to be
numbers.
less than 120?
Yes, you should
But
know.
you just need to know less than 120.
Right, because really every compound is going to be different. So those angles are given for the absolutely symmetric compound, but every compound is actually going to be slightly different. And so to know the actual number, the only ones that we're going to look through actual numbers really is water and some of the oxygen ones. But so we just say that we know they're going to be less than that because we know the electron group is pushing it away. All right. Questions? Other questions about that? Make sense? Okay. So moving on to the next shape, if we add a fourth group, we would not, so this is actually 5, but we would not have this shape, but rather this three-dimensional shape that you see over here called tetrahedral. Why do you think that is? Why doesn't it make this nice symmetric T shape or cross shape or plus shape?
Because it's still 90 degrees and 109.5 is greater than 90 degrees.
Yeah, same. So we have 3 dimensions to work with because the molecules exist in space, so we might as well use them. If we have a flat structure like we drew here, those are 90-degree angles. That structure over there is about 110. And this always kind of drives me crazy. I mean, it doesn't really drive me crazy. It's not that big of a deal. But books always do this. They always report the tetrahedral angle as 109.5 degrees, which is true. The angle in methane, which is a perfect tetrahedron, is 109.5 degrees. But I don't know why we need so many extra significant figures just for the tetrahedral one. It's just about 110. Because just like anything else, depending on the compound, it's going to be a little bit different. So I don't know why we always have to go up to 109.5 there. I just think about it as about 110.
Can we say in a test 110?
Yeah.
Or a quiz? That makes
Yeah, you can. And then just as with the trigonal planar, as we add lone pairs to that central atom, like ammonia and water, we're now pushing that angle away, and we now have less than 110 degree angles. Less than 109.5, if you want to say that. All right, so another thing that we have to keep in mind here that can be a little bit tricky is you'll notice a few different columns going on here in this table. The electron groups is what we've been talking about. So we talked about the 2 electron groups being linear, the 3 being trigonal planar, the 4 being tetrahedral, and the 5, we haven't gotten to the 5 yet. But the thing that happens in reality is if we replace those atoms with lone pairs, we're really changing the shape of the molecule. Because even though we can draw this like this on paper to show that there's 3 groups, in reality we don't see that lone pair. That's still just in the orbitals on the central atom. So it can be useful to talk about the actual physical shape of the molecule rather than just the geometry as dictated by all its groups. So we define 2 different ideas, the electron geometry and the molecular geometry. The electron geometry is the consequence of the this idea of electron pair repulsion. If everything wants to be as far apart as possible, what shape do you get? So if you have 3 groups, they all want to be as far apart as possible, you get a trigonal planar arrangement. If you have 4 groups, they all want to be as far apart as possible, you get a tetrahedral arrangement. And so on, and we'll get into the bigger ones later. But the actual shape of the molecule is something we might also want to know. So that's where that next column comes in. If we have a molecule like SO2, even though that lone pair does take up space, because we don't see it in the actual shape of the molecule, we need a name for the actual shape of the molecule, and the name for that is bent. So the electron geometry is still trigonal planar, but now the molecular geometry is called bent. When we go to 4 electron groups, we have the same thing, but because we have more electron groups, there are more different possibilities for molecular shapes. So those would all be called a tetrahedral electron geometry because they all have 4 electron groups, whether those groups are bonds, so atoms, or lone pairs. But the molecular geometry is going to change based on how many of those are lone pairs and how many of them are atoms. If they're all atoms, we still call that tetrahedral. If it has 1 lone pair, we call it Trigonal Pyramidal, so it's like a triangle pyramid, and that's like the ammonia structure, so you can see that here. Nitrogen in the middle with 3 hydrogens, and you can see that it has the same type of structure as a tetrahedral structure, but missing one of the groups, and that remaining structure has a different shape to it, and a different physical shape, and that's where that word Trigonal Pyramidal comes from. And then if we had another lone pair, once again, we change the shape, the actual physical shape again, and we call that one bent, just like we call this one, but they're bent at different angles. So the shape is the same, but the angle is going to be a little bit different. The angle in water is about 104.5, so you can see it's quite a bit down from the ideal tetrahedral angle. All right, so any questions about that idea? That we find the electron geometry from the total electron groups around the central atom. Then as we replace the atoms with electrons, with lone pairs, we change the shape because we don't see the electrons. Probably the hardest part of doing this is just remembering all the different names, because they're not necessarily names that you've seen or used before. So things like tetrahedral, trigonal pyramidal. I assume you've heard the word bent before, but some of these other ones may be new. All right.
Not sure one that was called the seesaw of the molecular geometry of SF4.
Yeah, we'll get into these bigger ones now. Seesaw, it's like a thing that they describe it. One person sits on one side, the other person sits on the other side, and it goes like back and forth like this.
Yeah, I know what a seesaw is.
Okay, so that's the idea is that's what that shape would be, but like kind of turned on its side. That's why it's called that. Yeah.
If you didn't draw it on its side, would that be a big deal?
No, because as you can see, well, no, you draw however you want to draw it. When you're drawing the structure, it doesn't, as long as you've got the connections and the geometry right, that's what's important. So the most possibilities for different shapes come with the largest, but also the most asymmetric structures. And the one that probably gives people the most trouble is the one with 5 groups, which is called Trigonal Bi-Pyramidal. So I'll leave that up there and draw this on the board over here. The reason this one gives some trouble is because it's the only type of shape that we talk about that has 2 different angles, and so it may not be immediately intuitive which ones you remove when you replace the atoms with electrons. So let's take one like PCl3, like they show there. But one way that we sometimes express 3-dimensionality on 2-dimensional surfaces in chemistry is by using what we call dash wedge notation. If we draw a stronger, like kind of colored in bond, sometimes kind of triangle shaped, that's meant to express that that atom is coming out at you. And if we use a dash bond, that's meant to express that it's going backwards into the board. All 3 of these atoms are meant to be in the same plane. They're meant to be coplanar. This one would be directly in the plane of the board, this one coming out at you, that one's going back. So if you were to look down from here, what shape would that look like? If you were looking from the top or from the bottom, that would be, yeah, a trigonal planar or a triangle. So if you connected all these, it would be a triangle. But this is really the same geometry as the trigonal planar geometry we saw earlier, the 3-group geometry. We're just sort of tilting it sideways. So then a bipyramidal structure will also have 2 more that are called the axial substituents, or the axial atoms. These are known as the equatorial, and the others are known as the axial. So around the middle here, we have the equatorial atoms, and on top and bottom we have the axial. And those are actually, within their group, they're interchangeable. So they're equivalent positions. Even though we draw one over here and 2 of them over on this side, we could have just as easily flipped that or drawn it. However, these 3 are all interchangeable. And then these 2 are interchangeable with each other. There's no top or bottom, except as we drew, the way that we read our P, but we can imagine flipping the whole thing over and having the same thing. So these are 2 equivalent positions, these are 3 equivalent positions, but they are not equivalent with each other because the bond angles are different. We can always tell the axial substituents from the equatorial ones. So this bond angle here is 90 degrees, as is this one, as is this one, as is this one, and so on. So any angle between an equatorial and an axial atom is 90 degrees. The bond angles around the equatorial atoms are 120 degrees, just as you said, just like trigonal plane. So this structure actually has 2 different angles in it. All right, so then that complicates this next question a little bit. If we are to replace an atom with an electron pair, so let's say we go to a structure like SF4, where do we put that electron pair? With the previous structures, tetrahedral, trigonal, planar, it didn't matter where we put the electron pair because all the positions are equivalent. But now all the positions are not equivalent. We have a very different structure if we put an electron pair at an equatorial position versus putting it on an axial position. So which one does it go on? I mean, you can see on the chart, but yeah. Right, so the equatorial positions, the electron goes there. This is not going to be the right structure because we didn't change our other atoms. But the reason the electron goes there instead of here is these axial atoms have 3 90-degree interactions, 3 90-degree angles. The equatorial positions have 2 90-degree interactions and then 120 degrees, which is farther away. So there's less repulsion if the electron pair goes onto the equatorial position instead of the axial position. And then just as with all the other structures, we would expect that these angles now on the other side of the lone pair become a little bit smaller as everything kind of gets pushed away from the lone pair. So then if we had a second lone pair, where would you expect that to go? The lone pairs always want to be as far from each other as they can. So where is it as far from that one? Is it another equatorial position or an axial position?
Equatorial on the potentially 2 scales. Or not on the 2 scales, but on the wedge and the little dot there.
Yeah, so we'd want to replace one of these other equatorial ones, because if we replace an axial one, then we have this really close range 90-degree interaction between the lone pairs. So for those lone pairs to be as far apart as possible, we replace another equatorial position. And then that makes actually, even though it looks a little weird from this angle, that makes just what we call a T shape. So that is that T shape that we said we didn't have in the trigonal geometry, because now we have to make room for those lone pairs, and so the rest of the atoms we expect to make that T shape. And then if we had a third one, which only happens in some of these kind of weird noble gas structures, we would replace the third one, and then we just have a regular linear structure. Yeah.
And notice you originally had it T-shape like that.
Yes, that's equivalent to this. So these positions are all equivalent. So it doesn't matter which ones you put where. Yeah. All right, so that position, or that type of geometry usually gives people the most trouble because there are 4 different geometries that you have to think about. Trigonal Bi-Pyramidal, seesaw, T-shaped, and then linear. How come there are more different types of shapes in Trigonal Bi-Pyramidal than in Octahedral, which has more atoms?
Because there's an odd number.
Yes, so what's the consequence of that?
They're not going to create right angles.
Well, yes, that's true. It's the asymmetry.
Yeah.
So the fact that in the sixth position structure, like octahedral, because all the positions are equivalent now, just like the smaller ones, all the positions are equivalent. So we don't have this issue of like asymmetry of putting the electrons on one position versus the other. It once again stops mattering which position you put the electrons on. They're all equivalent. And that in itself can be a little tricky, because if you look at the octahedral structure, which looks like that, and it's named because if you imagine the outer atoms connected to each other, you make the geometric shape called an octahedron. It doesn't look like a perfectly symmetric structure. It looks kind of like this, where you have axial and equatorial substituents, but it's not. Those are all equivalent. An octahedron is a regular solid, which means it has all equal sides and angles and stuff. So if you rotated that up, like if you took this atom here and pushed it up to there, and made this one come down here, you'd have that same structure again. You can rotate that however you want. All those positions are equivalent. So that means that when we start replacing atoms with electrons, we can put them wherever we want. So we take one off and we get what we call a square pyramidal structure like this. So that's missing this one. And then the second one we replace, we're going to replace the opposite, because then those electrons are as far apart from each other as possible. So one electron pair here, one down here. And that gives us a square planar geometry. If we could replace one more, we'd get back to a T-shape, but I don't think we'll see that in real structures. All right. So any questions about all of that? We'll practice it a little bit. One more thing that they didn't really talk about here, a little bit up here. This idea of electron groups does not change based on the number of, or the multiplicity of the bonds. So a single bond, double bond, triple bond doesn't matter. That still counts as one electron group on that side. So if you take a structure like SO2, you've got one group here, and then the lone pair is the third group. So that's 3 groups. The double bond doesn't count as 2. Same thing with CO2. Each of those counts as 1 group, not 2. All right, let's try some. So for each of these structures, I want the electron geometry, the molecular geometry, the approximate bond angles, and that'll be good for now. Then we'll get into the tetrahedron later.
Can we have a little series to work with?
A what?
Can we have a little things over there?
If you want, but you have to know the electron geometry. You have to know this before you do those, because they're different. So you have to like pick one that has the right geometry. But yeah, you can grab the models if you want. All right, so try PCl3. ICl4 ion. And BRF3. We can draw those out. See if you can do it without the chart. If you don't, you should be able to do this without the chart, except for remembering the words and maybe the angles, you know, the names of the things. But see if you can still kind of draw what you think that structure should look like, even if you don't remember the names from the chart. another minute or so to get these, and then we'll talk about them together. All right, let's take a look, see what if I get what you also get. So, as you can probably figure out, or as you probably figured out, you have to get the right Lewis structure first before you have even a chance of getting the right geometry stuff. So first goal is to get a good Lewis structure. For PCl3, that's going to be chlorine's got 7 valence electrons, so 3 of those, 21 plus 5 for phosphorus is 26 total electrons. When you first draw it, just don't worry so much about the geometry. Just draw it however you want to draw it that makes it so you can make a good Lewis structure. Let's get our electrons on there. All right, fill up the octets for chlorine, and then I've got 2 more for phosphorus. I think that works. Was that Lewis structure you got? Hopefully. Okay. So now that we've got the Lewis structure, we can start thinking about the geometry and all of that. This one, how many electron groups are on the central atom? 4, right. We've got the 3 Cl's and then the lone pair. So our electron geometry is called tetrahedral, which always is the one that goes along with 4 groups. That means that our bond angles are going to be around 110, a little less because of the lone pair. For our molecular geometry, we imagine a tetrahedron but missing one spot, and we get something like this. And what's the name of that type of geometry? Yeah, careful. It's Trigonal Pyramidal. Bi-Pyramidal would be the one with 2 pyramids, so the one that has 5 total things connected to it. So it's Trigonal Pyramidal. And we would expect these bond angles to be just less than 110 degrees because of the electrons pushing down on the...
So you don't have to say
On there.
109.5, you can just say...
You don't have to say 109.5. We don't need that level of precision here. On the final, it probably will say 109.5, but it's multiple choice, so you can probably figure that that's about 110, right? Okay. ICL4, same idea. We got to get the right structure first. So we're going to connect our atoms like this, and it is a negative ion, so that means we've got 36 total valence electrons. We've used 8 so far. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Is that what you got?
Yeah.
All right, great. Total electron groups there? 6. So what does that make our electron geometry? Octahedral. So then if we are to draw this, we're going to put the I in the middle. And our octahedral geometry means that our electron groups are going to take opposite positions on the octahedron. And that leaves us with this kind of a geometry. which we call square planar. And our bond angles are 90 degrees. They're not affected by the lone pairs really here in terms of pushing or pulling one way, because we've got one lone pair on each side, kind of above and below the plane, and then the square planar, those atoms are all in the plane. Yeah.
So you don't have to use dash wedge notation?
You don't have to. It can be helpful, if you want to express that. In this case, the way I've got this drawn, I would put wedges in front, and then the dashes kind of behind. But, you can draw this in any orientation you want. So you could draw it looking flat on, where it would just be like a cross shape or an X shape if you did it that way. There's no right or wrong way to express this, but you want it to be clear to a person that what the geometry is that you're trying to show. All right, and then finally BRF3. That one's going to have 7 valence electrons times 4 atoms is 28. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Did I count that right? Do I need one more? So let's try that again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yeah, 28. I need one more. There we go. Okay, so how many electron groups there? 5. And we call that Trigonal Bi-Pyramidal. We've got 2 lone pairs of electrons. So a trigonal bipyramidal orientation geometry looks like this. Right? And we've got 2 electron groups, so we're going to put those on the equatorial spots and put the atoms on the other equatorial spot and the 2 axial spots. Like that. So that our overall geometry becomes T-shaped. And those bond angles should be just less than 90 degrees because the electrons are going to be pushing on them a bit. All right, everybody see how that works? Maybe kind of. Okay, let's take a break, and then we'll come back and talk about valence bond theory, hybridization, and molecular orbitals. Yeah, let me stop the